Hello, everyone. It's me, Mr. Younger. I've made this attempt to calculate this a couple times in class, and I keep dropping a sign here, dropping an exponent there, or something goofy. So I wanted to go ahead and compute this average velocity of a molecule in a distribution according to the Maxwell distribution. So let me start off by going ahead and sharing my screen with you guys. What we're going to do is share my iPad screen. So what we're using is the Maxwell distribution. And what Maxwell was able to do was he was able to calculate the probability f of v that when multiplied is probability density, the probability density f of v that when multiplied by dv gives you the probability of finding a particular molecule in the gas at a velocity between v and v plus dv. This f of v was determined to be 4 pi times n, where n is the total number of molecules, multiplied by m over 2 pi kt, where m is the mass of the individual molecules, the mass of each one, and that's raised to the 3 halves power, times v squared e to the negative mv squared over 2 kt. That is f of v, and we know some things like the integral from 0 to infinity of f of v dv is equal to n, because n is supposed to be the total number of molecules in the sample of gas and of ideal gas. And if you're actually integrating the probability density f of v from 0 to infinity, that covers all the velocities. So all the particles should come out, and lo and behold, you get n. Because of that, we also do calculations like this. For instance, if we want to know the average velocity, we take and multiply by 1 over n, and then we integrate from 0 to infinity of v times f of v dv. Or similarly, if we want to know v squared bar, we're going to multiply by 1 over n, and then we're going to integrate from 0 to infinity of v squared f of v dv. Of course, that also means that when you're done with that, if you want the root mean square, you got to take the square root of it. What we're trying to do, though, is calculate this v bar, not the v squared bar. That can be done the same way. In order to do it, we will need the integration by parts, and integration by parts that I'm choosing to use, and the symbols that I'm choosing to use them, is the integral of u d omega is equal to u omega minus the integral of omega du. Now, often the trick with using integration by parts is to choose d omega to be a quantity that's easily integrable. So you don't necessarily, that doesn't mean just the dv that or the dx or whatever you have. That's almost never the case. But you grab something that would otherwise be really difficult to deal with, but because you're getting rid of this big chunk that's integrable, you can use it. So that's often the trick, and that's the trick in this particular problem. So I'm going to go ahead and calculate the average velocity like this. So the average velocity is 1 over n times the integral of v, now times 4 pi n times m over 2 pi kt to the 3 halves power times v squared e to the negative mv squared over 2 kt dv. As you can tell, all those constants out in front can go ahead and disappear. This n's going to cancel out, and I can put all those constants out in front, and I will get 4 pi times m over 2 pi kt to the 3 halves power times the integral from 0 to infinity. Technically, that one was also integral from 0 to infinity of, now I will have v cubed e to the negative mv squared over 2 kt dv. Now, what we want to use is the integral of u d omega equals u omega minus the integral of omega du for just this integral portion. So that's what I'm going to do. And in order to do it, I'm going to say let d omega equal. Remember, e to the negative mv squared over 2kt is not that hard to integrate unless you're integrating with respect to v and you don't have a v down in front. So what I'm going to do is I'm going to make d omega be v times e to the negative mv squared over 2kt times dv. So it is something that's easily integrable, and to show you it's easily integrable, I'm going to integrate it by using omega equals the integral of d omega, which equals the integral of v e to the negative mv squared over 2kt dt. This time I'm going to let x equal negative mv squared over 2kt, which implies dx is equal to negative 2mv over 2kt dv, which implies dv is just going to be negative kt over mv times dx. So now I can say omega, which equals the integral of v e to the negative mv squared over 2kt dv becomes integral, and this is from zero. Technically, I'll just leave it as a regular integral without the limits of integration. This is going to become negative kt over mv times the v that was already there times e to the x. And you can see that the v that was already there cancels out with this v, and I get instead negative kt over m times the integral of e to the x dx, which is just negative kt over m e to the x. So that's really what our result is. Now I can go ahead and continue using my integration by parts by seeing the integral from 0 to infinity of v cubed e to the negative mv squared over 2kt dv is going to be my u. I haven't yet chosen my u, so I need to do that. I already chose my d omega, so now I'm also going to choose u is going to just be equal to v squared, which implies du equals 2v dv. So now I can use u omega. So my u is v squared. Oops, I need to put that back in blue. Sorry about that. My u is v squared. My omega is negative kt over m times e to the negative m v squared over 2kt. That has to be evaluated from 0 to infinity. Now it's minus the integral of omega du. And of course, omega, we've already figured out, was in fact negative kt over m times e to the negative m v squared over 2kt. And now I have to multiply that, of course, by the du, and the du is 2v dv. So if you look at this specific product here. As v approaches infinity, the e to the negative mv squared goes to negative infinity way quicker than the v squared does. So that ends up giving you zero. And then when you plug in v equals zero, you also get zero. So this quantity is just zero minus zero. So that has no bearing on it. But the negative in front of the integral, which also, by the way, the integral is from zero to infinity as well. But the negative in front of the integral is going to combine with the negative in the kt over m. So I'm going to get that this is just equal to positive kt over m uh, times the 2, which I'll pull out in front, times the integral from 0 to infinity of v e to the negative mv squared over 2kt dv, and we just integrated that. We know, in fact, it becomes negative kt over m times e to the negative mv squared over 2kt. So we can go ahead and replace that. That's going to be 2kt over m from the 2 and the kt over m that was already in front of the integral. Now I've got to put a negative kt over m for what would happen if we did the substitution of, letting x equal negative mv squared over 2kt and taking care of that part. So this is all working out to be that times the integral negative mv squared over 2kt, and that's going to be evaluated from 0 to infinity. So we're actually in a pretty good spot right now. All we have to do is go ahead and combine this stuff. So now I have 2, and I have a negative, and I have a k squared, and I have a t squared, and I have a m squared in the bottom. And now I need to evaluate e to the negative mv squared over 2kt as v approaches infinity. And in that case, you get the limit as v approaches infinity of e to the negative mv squared over 2kt minus e to the negative 0. So that's the whole integral. Of course, e to the negative mv squared over 2kt, and the limit as v approaches infinity is just 0. So basically, this whole quantity inside the bracket is 0 minus 1. So the 0 is not going to do anything, but the negative 1 is going to make this a positive. So now I have 2 k squared t squared over m squared, all of that just times 1. And now all I have to do is take this and put it back with the original statement. So let me use my little lasso tool. I'm going to lasso this and copy it on the next page. Copy. Flip to the next page, say paste. And that's going to be what we have for it. I'll put it over here. That'll give me enough room. Now I can get rid of this extra stray. Ooh, I can get rid of this extra stray mark by killing that. And of course, now I can get my pencil back on. And this is V bar. We just figured out what this result of this integral is. This result of this integral, as we can see, turned out to be 2k squared t squared over m. So I'm going to say this becomes 2k squared t squared over m squared, like that. So now all I have to do is combine like terms and reduce exponents and stuff of that sort. So I'm going to go ahead and make this 4 into 2 squared. So that's going to be 2 to the 2 power. And I already have another 2 over here. I'll deal with that in a second, though. I have a pi from the one next to the 4, but I also have a pi in the denominator, and that's raised to the 3/2 power. So this is going to be 1 minus 3 halves, the minus because it's in the denominator. My m is going to be raised to the 3 halves power. My 2 in the bottom here is going to be raised to the negative 1 power. I've already taken care of my pi. My k is into the negative 3 halves power, and my t is also to the negative 3 halves power. And now I have yet another 2, and then a k to the 2 power, a t to the 2 power, and a m to the negative 2 power because the m is in the bottom. So let's continue working with this. Now I have 2 to the 2 minus 1. That takes care of this one and this one. Plus 1. That takes care of that one. And oh, there's also a 2 to the negative 3 halves. Oh, that's what I didn't get. I wrote it as 2 to the negative 1, but that's actually 2 to the negative 3 halves. Now you see why I keep making these careless mistakes. Sorry about that. So here's the 2. I've got a 2 to the 2 power, and what I found was wrong was this 2 to the negative 1. That was the careless mistake I made. That's supposed to be 2 to the negative 3 halves because it was in the denominator, hence the negative, but it was also raised to the 3 halves because it was in parentheses. So this becomes 2 to the 2 power. That takes care of the one I have checked. Plus 1, that takes care of the other one I have checked. And then minus 3 halves, so that takes care of that one. Now I also have pi. I'm going to say this is to the 4 fourths, or excuse me, I'm going to say this is to the 2 halves minus 3 halves. That takes care of this guy. And then I've got a m that's going to be to the 3 halves power, and then minus 2, and 2 is 4 halves, so I'm going to do it that way. Now I have k to the negative 3 halves. That takes care of that one. Plus 2, which of course k to the 2 is the same thing as k to the 4 over 2, so that takes care of that one. Now I've gotten rid of the m to the 3 halves and the m to the negative 2, and now all I've got is the t to the negative 3 halves and the t to the negative, or t to the 2, which would be plus 4 halves. So now I can simplify this a little bit. 2 plus 1 is 3. So that's basically going to be 6. That's 2 to the 6 over 2 minus 3 over 2. This is pi to the 2 over 2 minus 3 over 2 is negative 1 half. The m is to the 3 over 2 minus 4 over 2. That's negative 1 half. And the k is to the negative 3 halves plus 4 halves. That's going to be to the 1 half power. And the t is going to be negative 3 halves plus 4 halves. That's also going to be to the 1 half power. So I finally got my result. V bar is equal to, notice all of them have a fraction of 1/2 in it. That means a square root. So I'm going to write the square root here. But as I said, this 2 to the 6 halves minus 3 halves is going to be just 3 halves. So that is 2 to the 3rd under a square root. So that I'd write 2 to the 3rd, which is actually 8. That's why I almost wrote 8 there, divided by pi, and then it's also going to be times k times t over m square root. This becomes the square root of 8 over pi kt over m, and that's it. That's the derivation of the average velocity using the Maxwell-Boltzmann or the Maxwell distribution. I hope that helps. Have a good day. Bye bye.